You've seen it a million times, right? In every single science classroom, that big, iconic chart of boxes and letters. But you know what? The periodic table is so much more than just a poster on the wall. It's really a masterpiece of scientific logic. Think of it as a complete guide to the building blocks that make up, well, literally everything.
So let's just stop and think about that for a second. How on earth would you organize the entire universe on a single page? I mean, where would you even start? That was the huge kind of overwhelming challenge facing chemists back in the 19th century. They were trying to make sense of the absolute fundamental ingredients of matter itself. Okay, so before we got this elegant map, the world of chemistry was, honestly, a total mess. Just imagine you're discovering dozens and dozens of completely unique substances. Each one has its own weird properties, but you have absolutely no idea how they all fit together. It was just chaos. So, you had scientists just grappling with this ever-growing list of elements. Their first instinct? Okay, let's try organizing them by things like atomic mass. And look, that was a decent start, for sure, but it was kind of like having a list of all the parts of a car without any instructions on how to build it. They were desperate for some kind of grand unifying principle to tie it all together. And this is where our hero enters the story, the Russian chemist Dmitry Mendeleev. See, while pretty much everyone else was looking at this confusing jumble of elements, Mendeleev, he saw something different. He saw the faint outlines of a hidden pattern, a really deep logic that connected everything. Now, what's really fascinating here is that this was kind of like a race. Mendeleev wasn't totally on his own. Other scientists, like Julius Lothar Meyer, were hot on his heels, working on similar ideas. But what made Mendeleev's work a total game changer was his incredible confidence. I mean, he didn't just organize the elements they knew about. He had the guts to leave blank spaces, gaps in his table, for elements he was absolutely convinced had to exist, even though no one had found them yet. That was bold. And this is where you can just see his genius in action. Check this out. In 1871, he predicts the properties of an element he called Eka aluminum. Okay, fast forward just 4 years later, and boom, the element gallium is discovered. And its properties? They were an almost perfect match. Just look at the predicted atomic weight versus the real one. And the density? Spot on. This was the ultimate proof that his table wasn't just some tidy little chart. No, it was a ridiculously powerful predictive tool. This was a huge moment for science, period. You have a theory, you make a bold prediction, and then it comes true. I mean, you can just feel the pride in his words here, can't you? This wasn't just about being right. It was the validation of his entire life's work, proving he'd uncovered a fundamental law of nature.
Okay, so how did we get from Mendeleev's blueprint to the modern table that we all use today? Well, let's take a little tour of the finished building, so to speak, and decode its really elegant design. All right, the pure elegance of the modern table really just comes down to its structure. It's all neatly organized into horizontal rows, which we call periods, and vertical columns called groups. You'll also see these larger regions we call blocks. But what's the one simple rule that governs this whole thing? Remember, Mendeleev used atomic mass. We now know the real organizing principle is something even more fundamental. And here it is, the atomic number. It's simply the number of protons in an atom's nucleus. That's it. Every single element has a unique proton count, starting with hydrogen at number 1 and going all the way up to oganesson at 118. This one number, it dictates everything. So those horizontal rows, those are the periods. As you move from left to right across one, you're basically just adding one proton and one electron at a time, building up the atom. And every time you drop down to start a new row, you're actually starting a brand new shell for those electrons to live in, a little further out from the center. Now, the vertical columns, the groups, this is where the periodic part of the name really starts to make sense. The best way to think about them is like chemical families. All the elements in the same group have the same number of electrons in their outermost shell. And because of that, they tend to behave and react in really similar ways. It's like, they have similar personalities. Group 17, the halogens, super reactive. Group 18, the noble gases, famously aloof. They don't like to mix with anyone. And finally, you'll see the table is carved up into these big rectangular blocks, S, P, D, and F. These are basically neighborhoods, and they correspond to the shape of the orbitals. That's just the fancy word for the regions where an atom's outermost electrons are hanging out. So the table is literally a visual map of an atom's deep down quantum structure. Pretty cool, right?
But here's the thing, the table's power goes way beyond just being a neat filing system. Its structure is so logical that we can actually predict how an element will behave just by seeing where it lives on the map. These are like the building's smart functions. We call them periodic trends.
All right, let's start with atomic size. Now, common sense would tell you that as you move from left to right, adding more protons and electrons, the atoms should get bigger, right? Well, get this. It's the complete opposite. They actually get smaller. Why? Because that stronger positive charge from the extra protons in the nucleus pulls all the electron shells in tighter, kind of sucking everything in. But if you go down a column, you're adding whole new shells so the atoms totally balloon in size. Wild, huh?
And you know what? The exact same logic applies to something called electronegativity, which is basically just how greedy an atom is for electrons. As you go across a period, that stronger nucleus gets better at attracting new electrons, so electronegativity goes up. But as you go down a group, the outer electrons are so far away from the nucleus that its pull is way weaker. Once you see the pattern, it all makes perfect, predictable sense.
Okay, so you might be thinking, great, a perfect, settled system. But not so fast. You see, the periodic table isn't some finished monument set in stone. It's actually a living, breathing document with active renovations and some surprisingly heated arguments. As of today, we've officially got 118 recognized elements on the books. That fills out the first 7 rows of the table completely. But here's a wild fact to keep in mind. Everything after element 94, plutonium, you can't find it anywhere in nature. It's all purely synthetic, man-made stuff created one single atom at a time in massive particle accelerators. So, does that mean the map is finally complete? Nope, not even close. Even with all 118 boxes filled in, scientists are still arguing about where some of the most basic pieces of the puzzle actually belong. I mean, take a look at hydrogen. It's got this one outer electron, which makes it seem like it belongs with the group 1 alkali metals. But sometimes it acts more like the halogens over in group 17. So, should it just float all by itself? And what about helium? It acts like a noble gas for sure, but its electron setup technically puts it right above group 2. And don't even get me started on group 3. Chemists are in a huge debate about which element should go there. It just goes to show you that science is never really done. It's always questioning and refining itself. And it doesn't stop with just debates. The quest for more is still on. Right now, physicists are smashing atoms together, pushing the limits, trying to create elements 119, 120, and even further. What they're really hoping to find is this theoretical island of stability, a kind of holy grail where these new, super heavy elements might actually stick around for more than just a few fleeting microseconds. And that leads us to the final, absolutely fascinating question. As we keep pushing into this totally unknown territory of super heavy elements, will Mendeleev's beautiful periodic law keep working? Or will the truly bizarre effects of physics, like relativity, start to warp the rules on these massive atoms, breaking the pattern and forcing us to draw a completely new map of the universe? We'll have to wait and see.